Jan Chui, and Jan is an AWS serverless hero and has over 10 years of experience running production workload in AWS. He is the author of Production-Ready Serverless and co-author of Serverless Architectures on AWS 2nd edition, both by Manning. Moreover, he has also self-published other courses such as Complete Guide to AWS Step Functions and Learn some Lambda Best Practice for Great Good. Jan is a regular speaker at user groups and conferences internationally, like here, and keeps an active blog at theburningmonk.com, where he shares everything he learns about AWS serverless and chaos engineering. So please welcome on stage our next presenter, Jan Chui, with the presentation, Why Your Next Serverless Project Should Use AppSync. The stage is yours.
For joining us today. Let me just quickly share my screen, and so I can start the slides. Yeah, so my talk is going to be around why your next service project should be using AppSync. I guess the inspiration for this talk came from something that I worked on a while back. Because last year I worked for a client project where we built a new social network in just a couple of weeks using serverless technologies and using GraphQL. And we delivered something that was able to quickly help us scale to many hundreds of thousands of requests per day. And our AWS bill for that first couple of months when we first went live was only about $60, most of which was going towards the AppSync caching. And as you can see, we weren't spending very much on DynamoDB and the Lambda invocations because our caching was soaking up 99% of the requests. And the fact that everything went really smoothly, even though we delivered something very, very quickly, and we're able to having to scale pretty quickly as well. So we had some really happy customers at the end of this project. And I was only able to deliver all of this pretty much myself on the back end in a couple of weeks because I was able to stand on the shoulders of giants companies like AWS and Algolia, and using technology like GraphQL and the serverless components, which nowadays, I guess I would say AppSync, Lambda, and DynamoDB are my default stack for a lot of my projects, which gives me a lot of scalability, resilience, performance, and being able to build applications that is secure while also allowing me to be super, super productive as well. And I hope that at the end of this talk, you will feel the same way as well, and you will be tempted to give this stack a try. So my name is Jan Chui. I've been working with AWS for many, many years now. And since 2018, I'm also one of the serverless heroes as well. I guess my first journey towards serverless was maybe about 2016 when I worked for another social network, and we moved the whole social network to pretty much entirely run on serverless. And nowadays, I spend half my time working with Lumigo as a developer advocate. And the Lumigo is a troubleshooting platform for serverless applications, which makes debugging and troubleshooting your serverless applications super easy. The other half of my time, I work as an independent consultant, where I help other companies and businesses succeed using serverless technologies. In my free time, also written a couple of books and published a few video courses. And I guess I want to start by just quickly introducing to you what is GraphQL and how it differs from REST, which I'm sure most of you are familiar with already. So GraphQL basically contains two things. As the name suggests, it's a query language for your APIs that lets you describe what data you have and what you can do with the data. But it also needs a runtime component that can take a query written in this language and fulfill the query using the data you have in your environment. So every GraphQL API has a schema that defines what queries and mutations operations that it supports. So queries are for reading data and mutations are for writing and updating them. So a client will send a query or mutation to a GraphQL server who will then validate the request against the schema, and then you'll process the request. And this schema is basically the contract between the client and the server. And it's not just a piece of documentation that is generated from your server-side implementation, like many Swagger or Open API specs. What GraphQL schema doesn't just document the operations in a GraphQL that a GraphQL API supports. It defines them and is binding in terms of the types of data that can be sent and what data points can be returned by the API. So when the client sends a query or mutation to the GraphQL server, the server is going to validate the request against the schema. So the client can't ask for data that don't exist in the schema. And the argument that is sent has to be the right type and so on. And then it's going to map every single type of field to a resolver, which is responsible for ultimately fulfilling that request by getting data from the different data sources you have in your system, such as DynamoDB tables or RDS databases or Elasticsearch clusters. So if you compare that to, say, REST APIs, where you are making an HTTP request to a URL like this one, where the path follows some kind of a hierarchical structure that ultimately takes you to the data you're looking for. In this case, we're looking for the data for a user with user ID 1234, and it's going to return some data in JSON. And in this example, I'm loading a user profile. So the API takes the user's ID from the path as my argument and returns my profile as JSON. With GraphQL, there is only one entry point for all of your requests, and the convention is to use the HTTP post to pass the request arguments as the body. Another important difference is that as part of my request, I have to specify what are the fields from the profile resource that I want to be included in the resource. And because I can only ask for the, in this case, because I'm only asking for the first name and the last name, so those are the only fields that are returned by the server in the response. And the same will work if I've got other nested fields on the profile resource and other arrays as well. So for example, if there's a friends array on my profile, and I can say for each of the friends, what fields do I want to be included in the response? And so in this case, I can say for a profile that I'm fetching, with the ID 1234, I want the array of friends to be returned, and for each of the friends, I want to have the first name and the last name. And you can see the response matches that specific structure, and the GraphQL server can't return data that is not on a schema either, which means that you have a response validation out of the box, as well as a request validation as well. And the way it's really powerful is when you're building a real-world application, like a mobile app or web application, whereby you've got maybe like a screen like this one, where you're building a social network. There's a profile page where you can go and view your profile. And in this case, there's a whole bunch of different information you need to get from the backend to show your name, your location, some profile image, and some background image that you want to include in this particular profile page. And then maybe a list of the sports that you do and how good you think you are at each of the sports, which, as you can see, I'm not very good at any of them. In this particular case, so we're talking about a social network where you can organize the activities and invite other people to join them. So in this page, we also want to return the activities that I have organized, like a basketball match or maybe jogging in the park. And for each of the activities, I want to show when and where it's going to happen, and how many people have signed up to take part in my basketball match next week. So if I was to build this whole system using REST APIs, I would probably start by getting this user's profile, right? So I fetch the user's profile, but notice that the user endpoint returns a whole lot more data than we actually need to display in the UI. So we're getting a lot more data back than we actually need for our use case. So this problem is known as the overfetching, where we have to fetch data that we don't need, which wastes resources like bandwidth and CPU cycles for sending the data over the wire, but also for serialization and deserialization as well on both the client and the server. And worse than that, it also doesn't return all the data that we need for the UI, because we also need the list of sports, we also need the list of activities and so on. So we have to end up making additional calls to the backend to request other information from different endpoints to get details about each sport, so that we can display the correct image and the user right display name, and then list of users, and so on and so forth. So this adds a lot more round trips between the client and the server. And it's not always possible to do this in parallel, which then also add delay to how quickly we're able to render the UI, which ultimately is going to hurt user experience, so that when someone goes to view their profile page, it takes longer and feels sluggish. So this is known as the underfetching and the N+1 request problem, which is a major source for inefficiencies and waste when it comes to building real-world applications. So to mitigate some of these problems, a very common pattern emerged called BFFs, or backends for front ends, whereby, say, a front-end team would create dedicated APIs for just the UI page they're working on, and these backends for front ends would then act as a proxy to other APIs to help reduce the number of round trips between the client and the server. And to give the front-end team also more control as well over what data points are returned, and to mitigate some of the impact of overfetching and underfetching as well. But using this pattern, you do end up creating a lot of BFFs, which is maintenance overhead, and you also end up doing a lot of duplicated work, potentially duplicating the same business logic between different BFFs, but also duplicating logic between the BFFs and the backend APIs that they proxy to as well. And with GraphQL, there's essentially no need for you to write bespoke BFFs anymore. Certainly not every time that you need to work on a new UI page, since the client has a lot more expressive power to ask for whatever data they want and only get back the data that they actually need. So to implement the same UI page using GraphQL, I can ask for all the data I need for this particular page using a single GraphQL request, where, as an authenticated user, I ask for my profile, and I specify in the query that in the response, I want to get back certain data points. And in this case, AppSync is a fully managed GraphQL service that lets you build scalable GraphQL APIs without having to run any servers. So you can focus on writing those resolver logic that fetch data from where your database is or other data sources are. So in this particular query, I want my ID, my first name, last name, gender, and so on. So I'll tell AppSync in my GraphQL query that they should fetch this information from the data sources, and it's gonna based on my configuration in AppSync, is gonna say that, okay, you're looking for the profile, so I'm gonna fetch the profile data from the profile table in DynamoDB. And as part of this request, I'm also asking for each of the sports. I want the display name field as well as the image URL, which is not embedded into the profile objects themselves in the profile table, because we want to be able to say updates the image you want to use for a sport, say for basketball, without having to update all the users who has got a reference to this basketball sport. So instead, we have some pointers to another object that resides in a different database. So in this case, we will need to be able to get the display name and image URL from the sports table, which kind of like a join you would do in the relational databases, where we're joining these two tables by these two fields, which when it comes to NoSQL databases like DynamoDB, it's a bit awkward to say the very least. You typically have to do these kind of joins in your own application, where you're making calls to get data from different database tables and then combine them together. One of the great things about using GraphQL and AppSync is that this whole application level joining just happens for you by configuration. You don't have to do any custom code to do that yourself. And in this case, we're able to get the information from the sports table for the relevant sports that this particular user is interested in or is doing. And we can return just the name and the image URL from that table without exposing additional data that we may not want to, that we may record in the database table, but we don't want to return to the caller. So GraphQL and AppSync in this particular case handles all of that for us, and it maps those fields that are requested in the GraphQL query to fetch data from the profile table, and then for the relevant, for the, I guess, referenced sports, it fetches them from the sports table and is able to return just the data that the caller wants. So there's no need for the caller, for the client to send 2 separate requests, which ultimately saves us from those additional round trips, which would have added additional overhead, and it would have been necessary if I was to build this using REST instead. And for the list of activities, since I have many activities, these are all stored in a separate database table altogether in DynamoDB. There's a table called activities, which is away from my profile, but for each of the activities, it has a reference to the profile or the user ID. So I'm able to find my activities by doing a DynamoDB query against my user ID. So when a GraphQL query is asking for the activities that belongs to a particular user and information about those activities, then the AppSync API is able to fetch those additional information from that activities table in parallel to when it's fetching information about the profile as well as the sports. And again, it's able to join everything together and return that in one JSON response to the caller without you having to do all of that joining in your application code. We can also further expand the nested objects that we have in the request. So in this case, for each of the activities, I also want to find out, which are the people who have who are joining this basketball match, and I want to get their image and their and the first name for those users. So I'm able to also make that as part of my GraphQL request, and AppSync will resolve that by fetching those additional users' profiles from the profile table, as it did from my when you try to fetch the main user's profile. So as you can see, this is all very flexible. The client can basically ask for any information they need in a single query, hence reducing the number of round trips that need to happen between the front end and the back end. And you have a lot more control over on the back end in terms of caching behaviors and so on, which we'll talk a bit more later. And it solves the problem of overfetching and underfetching, and the client can ask for just the data it needs, nothing more, nothing less. And since the GraphQL schema itself is a strongly typed contract between the client and the server, which also kind of doubles up as a request and response validation. So the client can't ask for data that's not exposed explicitly in the schema, and the server can't return any data that's not in the schema either, which makes it much harder for attackers to try to steal sensitive data from your system. We've seen many cases of attacks in the past whereby a server application was tricked to return much more data than it was intended to. And because the schema really is just, say, the Swagger spec or the Open API spec, is just the documentation that's generated by the backend. It doesn't let you actually do any response validation. So if someone was able to execute a SQL injection attack, then they can potentially get all the data from your database. In the case of GraphQL and AppSync, that's just not possible because the server can only return the data that is explicitly exposed in the schema. So even if the AppSync API has fetched more data from, say, a DynamoDB table, it's just not able to return that through the API because those additional data points are not exposed in the schema. And it also solves one of the huge pain points for using NoSQL databases like DynamoDB, where there are no joins and you kind of have to do all the joins in your application code. So here, GraphQL and AppSync takes care of all of that for you as well, and is able to also execute things in parallel where possible, so that you can also get a lot of efficiency gains when query that can be executed in parallel as well. And with all things considered, GraphQL just makes it so much easier for you to build data-driven applications and then enable front-end teams to really quickly iterate on the product and user experience instead. And it has become my default choice for building new applications. And I really hope that after you've seen this, you will be convinced to give it a try at least. So let's talk a little bit about AppSync. So AppSync supports 5 different data sources out of the box. Firstly, you can have AppSync resolve part of a query, and by having an AppSync resolver send HTTP requests to any HTTP endpoint. So it's a great way for you to kind of put GraphQL in front of existing REST APIs infrastructures you have, so that you can, so that makes migrating your application to GraphQL a little bit easier, because you don't have to rewrite all of your APIs in one go, but instead you can just put the GraphQL layer in front of all of that REST APIs you have, and then migrate the UI pages to hit this AppSync API. And then over time, maybe you want to migrate the actual implementations for those REST APIs, so that you maybe don't need them anymore. You would just have the AppSync API fetch data directly from the data sources like your DynamoDB tables, etc., etc. It also supports DynamoDB out of the box, which is a highly performant and almost infinitely scalable NoSQL database that Amazon offers. It also supports RDS out of the box, or the relational database service from AWS. Oops, sorry, press the wrong button there. One thing I should mention here is that the AppSync integration with RDS only works with serverless Aurora v1 via the HTTP API. So as far as I know, serverless Aurora v2 is not yet supported yet. And because of this limitation, not all RDS database types are supported either. AppSync also supports Elasticsearch out of the box, which is useful for building full text search in your application. You can map those GraphQL operations straight to an Elasticsearch query, which is useful for, again, building full text search in your application. But maybe sometimes you want to use other services. For example, for search, I actually quite like to use Algolia instead of Elasticsearch. So what I can do is I can have a Lambda function instead, and then use that Lambda function to connect my AppSync API to other services, both AWS services as well as just other public services, third-party services like Algolia. AppSync itself is very scalable, and it also got a really scalable GraphQL subscription implementation, which is useful for building real-time applications where you want to send push updates to the client. And your AppSync API is automatically deployed to multiple availability zones out of the box, which also gives you a really good baseline for resilience as well. In terms of how you pay for it, you pay for only what you use at $4 per million query or mutation operations. So on paper, this may sound more expensive than some of the other things you find on AWS, like even API Gateway, which is about $1 or a couple, I think $1, $2 per million HTTP request. But because an AppSync API can run multiple resolvers in a single query operation, and all of that counts as one operation. As opposed to every time you run resolver, that's going to count as a separate thing. So whereas with REST, you end up having to, because of the under-fetching problem, the equivalent request would translate to at least several HTTP requests to API Gateway and to different APIs and to fetch different pieces of data, which would end up being more expensive because of, even though per million operations, API Gateway is cheaper than AppSync, but because you need fewer operations with GraphQL, so I think in practice, a lot of the APIs in production will actually end up being cheaper when they're going through AppSync than, say, API Gateway. With AppSync, you also, with GraphQL, one of the challenges is that all the requests go through a single entry point. So you can't just cache everything by the URL anymore. So it's kind of no caching at the CloudFront level for that matter. But AppSync has got built-in caching, which charges you extra based on the size of the cache node you want to use. Essentially, you're paying for uptime for a memcached node. But the good news is that memcached node is just fully managed. All you have to configure is that you want to turn on caching for AppSync and what's the size of the cache node you want to use. And you can either cache the entire request, or we can say, I want to cache results for specific resolvers. So AppSync gives you a lot of room to sort of mix and match here, and a good caching strategy can make a world of difference for performance and scalability, as well as for your cost. because even when you're running at a moderate amount of load, being able to return something from the cache as opposed to going through, say, a Lambda function and then going to a DynamoDB table means you can remove those costs associated with the Lambda invocations or the DynamoDB operations as well. AppSync's got built-in monitoring and loggings through CloudWatch metrics and CloudWatch logs. You can get high-level metrics like number of API requests, error count, latency, and all that, which is great. But unfortunately, all of these are aggregated at the API level, so you can't tell how well each of the resolver is performing. As we've seen, a single request can result into many resolvers being run as part of that request. So if one of them is slow, that caused the whole request to be slow, then it becomes harder for you to figure out just from this alone which resolver is the actual problem. So to get more information about what's actually happening in the request, you can enable logging, and if you turn the field resolver logs level to all, then you're going to get a world of information about what's happening for that request, and then which resolvers ran, how long they run for, what was the input and output for each resolvers. So there's a lot of information that can tell you, that can help you debug as well as to figure out any performance issues. And for visualizing some of the what's actually happening inside of request, you can also enable X-ray as well, which gives you like a bar graph for which operations for that say GraphQL operation and what's happening inside. As you can see, it's making multiple DynamoDB requests and some Lambda invocations. And in this case, you can see which requests to DynamoDB were made in parallel and which ones were made sequentially as well. And X-ray also shows you like a service map, so you can get like a high-level view of your service, of the services that your AppSync API is talking to, and their overall health. The problem with X-ray is really that it's kind of hard to find traces for specific GraphQL operations. So even though it's useful for giving you like a high-level overview, it's hard to actually debug specific problems for specific requests. And that's where tools like Lumigo comes in, which fills in a lot of the gaps. And for example, I can easily filter my traces by individual resolvers and individual requests as well. So AppSync gives me all of that. Plus, if you use Lumigo, then you get the tools like Lumigo, then you get additional observability. And the great thing is that I don't have to manage any servers, so I can get a lot more done with fewer developers than I could otherwise. Which is why I love this stack so much nowadays, that I, as an individual contributor, I can get so much more done using AppSync, Lambda, and DynamoDB, and I still get all the benefits in terms of having building something that is not just runs on my machine, but then it's going to crap itself if there's more than 100 people hits the API at the same time. I've got something that is both scalable and resilient and performant and secure, without having to sacrifice my own productivity. And even though serverless is not right for every single solution, but I think for a lot of the problems out there, you could build them. You can start building them with serverless components first, and until it's not good enough, then you move on to something else. Maybe move some of your workload to containers. But certainly, when it comes to building GraphQL APIs and building, I guess, modern data-driven applications, I think AppSync is a really good starting point. And with that, that's everything I've got. As I mentioned before, I'm a consultant, so if you need any help getting started with serverless components or looking for upskilling your team, then let me go to theburningmonk.com to see how we can work together. And check out my new video course, appsyncmasterclass.com, where I kind of show you how to use this stack to build something non-trivial. In this case, you're going to learn to build a Twitter clone using the technologies I just mentioned. And with that, thank you guys very much, and I hope you enjoy the rest of the conference. And let me know if you've got any questions.